Good morning, everyone. I hope you're having an awesome Tuesday. It is Halloween week. Whoop, whoop. So we are starting Unit 3, and we're going to be talking about forces this unit. So just like I did last time, as soon as I get everyone finished with the test, I will put up a slideshow with all the commonly missed questions and kind of go through some of that. So don't forget, you can retake one test per semester. We had Unit 1 and Unit 2. We will have Unit 3 and Unit 4 still. And then we'll take the final. The Unit 4 test will be like the week before the final. So I would suggest if you're going to retake one, probably choose from Unit 1, 2, or 3. So totally up to you. Just contact me if you would like to take advantage of that. You can wait until later if you want, so you know which one you want to take. So we are going to talk about forces today. We're going to start off with Newton's laws, this unit, and then let's see here. We're going to start off with Newton's laws. We'll have Newton's first, second, and third law. We're going to talk about the universal law of gravity, normal force, friction, Hooke's law, and then systems of objects. And then we will review and have our test. So I'm looking at right now having our test the week of Thanksgiving break. So that Monday, Tuesday would be our test day there. So go ahead and get through this. So we're in section 4.1. Like we don't have a book, but if we were using a book, that's kind of what we'd be going off of here. So success indicators, this is how you know if you're successful today. So after day, you should be able to describe how force affects the motion of an object and interpret and construct free body diagrams. Okay, so generally a fairly simple unit here. Okay, so we know that forces are going to be describing the interactions between an object and its environment. Okay, so these can cause accelerations. That includes decelerations. So when we're looking at this, if you look at the force diagram here on the side, you have a person riding a bike up an inclined plane. So you can obviously see where there are some angles involved. Okay, so you have the force of friction working backwards against his motion. You have his applied force is propelling him forward, which both of those forces are going to be at an angle to gravity, right? So they're at a 30-degree angle to gravity. They're parallel to the surface. You have the normal force pushing him upward, which we'll talk about, and then you have gravity and all these other motions involved. Okay, so this would be a very accurate force diagram to represent all of the forces involved here. Are there other forces maybe happening here? Sure, maybe there's some air resistance or something, but it's so minimal that we're not going to include air resistance for these. So you always draw an arrow away from the central object showing the magnitude and angle, just like all the vector diagrams we've done so far, describing his motion or the object's motion. So it's everything that could affect it. So if you look in the top right corner right here, this is how you would draw just the force diagram. You don't have to draw a picture every single time. You would represent the object with a small dot in the center or a square or however you want to do that, and then draw your arrows away from it. And you can see here that the magnitude of these lines is representative to the magnitude of the force. So the force of friction is less than the force of the applied force, which makes sense, right? Because if the force of friction was greater than the applied force, this guy would not be moving forward. The normal force is equal to gravity, which we'll talk about a little bit more. And then you have your gravity perpendicular to the surface versus just the regular force of gravity, which we'll get into. But this is a good example of where you would start kind of thinking about how you would draw a force diagram. So the unit for force is going to be newtons. Okay, so we're going to use newtons to describe that. It breaks down into kilograms times meters per second squared. Okay, so that's mass. Kilograms is mass times acceleration of meters per second squared. So what that really means is that 1 Newton is the amount of force that it occurs when the amount of force when acting on 1 kilogram, it produces an acceleration of 1 meter per second squared. So that part is not something you need to memorize or anything, but that's where the unit came from. So we named it Newton after Isaac Newton, who came up with these laws of his, but that's kind of the derivative of that. So weight is different than a force, okay? So a weight is a measure of the magnitude of gravity exerted on an object, okay? So weight and mass are not always the same thing. Okay, so if my dog Odie is a Bassador, so he's half black lab, half Basset Hound, so he's like short and fat and with these big ears. He's really cute. So anyway, he's kind of a hog. He likes to eat snacks, so he's a fat dog. So he's about like 65 pounds, right? So if I were to mass him, I would probably get his mass in like grams or kilograms, but let's just say pounds for right now. So if I were to mass him, I'd say that, okay, he is 62 pounds. Like that could be his weight. And then I would mass him and get his grams. So he has a weight on Earth because gravity is always pulling him down. It's pulling all of us down. But if I like shot him out to the moon and put him on the moon, his weight would be less because gravity is different on the moon. But he would still have the same mass, right? Like he's still a fat, cute dog. So weight is going to be the measurement specifically related to gravity. And we know that here on Earth, we're going to use gravity as negative 9.81. But there will be situations where you'll use a different gravity. You'll have a situation on like, in some kind of simulator with less gravity or on a different planet or something like that. So weight is specifically talking about the mass and the gravity together. So forces can act through contact or at a distance. So you have your two different kinds here. We have contact forces. They're going to be results for physical contact between two objects. Okay, so I'm pulling on a string. I'm catching a football. I'm pushing a desk across the floor. My son slapped me in the face. Like those are all contact forces. Okay, so something is physically touching something else. You are driving your car and your car is making contact with your tires or making contact with the ground. Field forces do not involve physical contact. So these are going to be things like gravity, electromagnetic fields. Okay, those would be the two main ones here. So you have these pictures on the side here of like the little girl that went down the slide. I'm sure this has probably happened to you if you've ever gone down one of these plastic slides at some point with like dry air conditions. So this girl has been affected by static, obviously. So that's an electromagnetic field. At the top picture, you have this man that's getting hit in the face with a soccer ball. This is actually a soccer ball full of water. They added water to it so that it would have more impact, more forceful impact. So you can see that this is definitely a contact force, right? Like look at his nose. This all goes back to normal. So there's a video for this, and I think I have it here at the end, and I'll show you. But if we don't watch this video on this lesson, go ahead and come back in here and watch this video because it's actually really funny. They just like throw stuff at this guy's head and watch it in slow motion. So if we're looking at this, we're trying to figure out, okay, what are the contact forces versus the field forces here? Okay, so you have some paper sitting on the table and you have some paper stuck to the balloon. There's a hand holding the balloon, right? So your contact forces are going to be the table supporting the piece of paper, okay? So you have a normal force from the table pushing up on the paper. There is going to be the person supporting the balloon, okay? So the person is holding on to that. You might say that there's some kind of frictional force between the paper and the table. Field forces here is going to be the gravitational force pulling everything down, okay, because gravity is not making physical contact with anything. It's just a force that exists. So gravity is pulling everything down. Then you have an electric force pulling up on the paper that's making it stick to the balloon. So you have your static there. Okay, so when we start drawing force diagrams, since force is a vector, force diagrams are going to represent the magnitude and the direction. Okay, so just like all of these vector diagrams, we've kind of been working up to this. We're just adding force into the mix. It's still going to come from the center. So if you have, like in this blue picture over here, you have a diagram of what's happening here. There's a person pushing a lawnmower. And then in the like lighter blue square, you have the force diagram. Okay, so you have like a drawing situation and then you have a force diagram. So they're not the same thing. So when you're asked for a force diagram, you want to give what's in this like little light blue situation there. So the tail of the arrow is going to be attached to the object on which the force is acting. So if you draw a circle in the center or a square, it does not matter. The tail starts there. The arrow is going to point in the direction that the force is being applied, which is not always northeast, south, or west. It's sometimes at an angle. The length of the arrow needs to be proportional to the magnitude of the force, and it should represent all forces acting in that situation. Okay, so with this this example here, we have a person pushing a lawnmower. Okay, so looking at the ground where its tires are on the ground, it's moving forward, right? So we have friction being applied against that applied force. Okay, so friction's being applied parallel to the ground backwards against his motion. We know that gravity is pulling straight down, and normal force is going to be the opposing force of gravity. So normal force always opposes gravity. That's why things don't like go crashing down through the desk. So if I set down my cup on the desk, gravity's not going to pull my cup all the way down through the desk into the earth, because there's the normal force pushing against that. So that keeps things where they are. So there's normal force being applied to you right now so that gravity does not pull you down to the ground. So anyway, so here we have gravity working against normal force, and we have its applied force. So if you notice where the applied force is on the picture versus in the force diagram, the applied force drawn in a force diagram needs to be shown from the object pointing away from it. So if we have a 30-degree angle being applied, you want to show that it's coming off of that object in the force diagram at a 30-degree angle. So other common types of forces, these would be how you would represent the variables. So when you're writing these out and you have force and you're trying to represent force, you do need to put the correct subscript on them so that you can identify what kind of force you're talking about. So we have gravity. The force of gravity is going to be Fg. Sometimes you'll see it as Fw, like F weight. Fg would probably be more representative of just true gravity, just like 9.81. F weight can be if you are specifically talking about the weight of something in a certain gravitational situation. Normal force would be Fn. Okay, so normal force and gravity are going to be involved in everything. They will always be there unless it says specifically to remove gravity. So normal force will always be opposite of gravity. Applied force would be F and then APP or FAP. That's going to be your applied force. So anything that is pushing the object in a direction, it's being applied to an object. Tension force is either Ft, or you could use a capital T. So we'll talk about this a little bit more later in the unit when we start talking about like pulleys and things. But this is going to be the force felt through a string or a cable when it's going to be pulled tight at the ends. And then we have frictional force, so F. So this is usually going to be in the opposite direction of your applied force. Air resistance will sometimes be involved. Okay, so it's kind of a special type of friction that acts on objects as they're going through the air. So air resistance is also noted as FF because it is a type of friction. And then spring force is F spring. They got really creative there on that one. This is going to be the force exerted by a compressed or extended spring on any object. So that's going to be Hooke's law. So we'll get into that towards the end of this unit. But these are your symbols that you're going to use. Okay, these are the symbols that we're going to use while we're writing our notations for things. So here's an example of a problem that you would do. So you're going to draw the force diagram. Okay, so here we have a dog is floating in a canoe on a lake. Okay, so the Earth's gravitational force on the dog is 760 newtons. Okay, so the gravitational force on the dog is 760 newtons because he has a mass and gravity's acting on his mass. Okay, so that's why it's not just 9.81. It's going to be the mass acting with the gravity acting on the mass. So 760 newtons downward. We have a gravitational force on the canoe is 190 newtons downward. The water keeps the canoe afloat by exerting 950 newton force upward. Draw the force diagram. So for this, we're just going to draw it right onto the dog on this one. If you were drawing this, you would want to just put a dot to represent the dog in the canoe. Okay, so we have F dog on canoe. I know this seems strange, but you could say like FG or FW, like comma dog, if you wanted to specify that you're talking about the gravitational weight of the dog or the gravitational force of the dog. So you have F of the dog, force of the dog is going to be 760 newtons downward. So I've represented that by this longer line here. Sorry, I let the little menu go away. Then the next one is going to be the gravitational force of the canoe, which I've done in green. So that's going to be the earth on the canoe. Okay, so the force of the dog on the canoe is 760, and then the force of the gravity on the canoe, or the Earth's gravity on the canoe, is going to be 190 downward. Okay, notice that they're drawn right next to each other and going in the same direction. That's how you'd want to show that. So you will have situations where you have multiple forces being applied in the same direction. Just draw them right next to each other. So this is why it's really important to label these and get the correct subscript notation. So then we have the normal force of the water, or the buoyant force, pushing everything up. That's going to be a total force of 950 newtons. So the size of the arrows are going to be proportional to the magnitude of the force, okay, which makes sense here. So if you notice, let's go back one. If you notice that the blue one is going to be equal to the 760 plus the 190. Okay, so you've got a force of 950 going upward, and a total force of 950 newtons going downward. That's why the dog is floating and not sinking or flying in the air. So for this one, let me see where we're at here. Okay, so this is going to be the very end of this video. I'll go ahead and show this. This video is like one of my favorites. So it's the slow-mo guys, and they are taking this soccer ball and like chucking at this guy's head and watching it in slow motion. So we'll go ahead and turn this on. Let's get the sound on here. Oh my goodness, I cannot get this to work. Okay, let's see if that works.
Earlier, Dan, I threw a ball at your head.
Well, apparently. I've seen the video, but I don't remember it at all.
Did it knock the memory clean out of your head?
I'm pretty sure my IQ point just went on the floor.
That was filmed at 1,000 frames a second, but today we have a camera that will do 28,000 frames a second. Let's do it again.
Maybe you'll knock the memory back into me with this one.
Maybe as this hits your head, you'll go back in time 6 years.
Yeah, I'll just forget everything since happened then.
We didn't really show this in the first video, but it's not easy to get water into a football.
Well, it takes time, because imagine you're pumping a pump and the air comes out, you just sort of go
Yeah.
Whereas because obviously water's thick and...
Well, water's going through a needle nose takes a long time.
So shove that back in there. So you just have to let the air out and then shove one of these needles in and fill it full of water.
I can hear it.
It's nearly rattle my brain. It hurts enough with a football full of air. Playing football, I don't head the ball.
Because it hurts.
Yeah, I'm like, why would I do that?
Well, you lose brain cells.
Exactly, I'm not doing that. I don't like the amount of times.
We're jumping a little bit here.
I just relaxed. That's got to be it.
Look at that nose. So much motion.
Right, do it again. Do it again.
Oh, God.
Wait until my eyes spin open for a few tries, okay?
For a few tries? Well, that's going to psych you out.
No, I found the zone. Found it, Pete. I've just imagined that you're shaking like a maracas next to me. And I'm not going to get hit. Right here.
It is a bit hot out. That was it. Yeah, look at that.
Okay, so for the sake of time, we're going to go ahead and close that. So let me see here. Let me escape out of that Get rid of that bad boy. All right, so hopefully that showed you that whole video. If it did not, please go back in and watch this video because it's my favorite. It's hilarious. So you guys have some practice work to work on Canvas. So you're drawing some force diagrams. There's not a whole lot of calculating or anything going on today, just a little. So get the practice done. Let me know if you guys have any questions, and I will talk to you next time.